we are once again hitting the edge of what I really understand versus what is market speak that is on the edge of my knowledge. If I think of a fixed income bond, then the value changes over time for multiple reasons. The amortized value will converge to the market value. We talked about market value back in chapter 4. Market value converges to maturity value. So I've got three different ideals of a value. I've got amortized value, I've got market maturity value, and I've got market value. Long-term changes are predictable. Short-term changes are all sorts of fluctuating. This is why people, quote, play the market to try and ride those short-term changes to their best advantage. But if I think about market value and yield to maturity, that's a discussion for what's going on in the market right then. How do people feel about the rates? But if I think about that rate and it changes, that can have a sudden, dramatic, substantial impact on market value. Unless you've got an annuity or a market implement, the security includes something about the yield, like a mortgage or a savings bond, where it's fixed for the entire length of the loan, yield fluctuates. So changes in market value change yield rates. How? Well, I'm going to walk through this first example in the text. Let's consider the spot rates for the next 4 years. R1 is 5%, R2 is 10%, R3 is 15%, and R4 is 20%. These are dramatically increasing. So this is a normal yield curve. Further out, the more it's worth. I'm going to say that we're going to assume this stays the same. As time continues. Now, what that means is if I buy something today and it's going to give back to me in 1 year, I'm going to earn 5%. If I wait a year and buy something then that's going to get back to me in 1 year, it's going to earn 5%, no matter when now is. Rates 1 year out are 5%. Rates 2 years out are 10%. Rates 3 years out are 15%. That's true today. That's true in 2027. That's true in 2026. That's true in 2028. So even as time changes, this set of rates continues to work this way. I have a zero coupon bond with a face value of 100. I want the book value and the market value in 1, 2, and 3 years. Okay. Book value and market value were discussed back in chapter 4. That's page 214. Let's think about right now, present value. I forgot to write something. I have a zero coupon bond face value 100, maturity in 4 years. I need that piece of information. Without it, I'm in trouble. So, what is the present value of this zero coupon bond? How much is this worth right now? Again? That's the face value. That's what it will be worth in 4 years. So this will give you $100 4 years from now. What do you pay for it today? It's a zero coupon bond, so I can think of it as a single deposit whose future value is 100. It's going to get compounded annually. And the 4-year spot rate is 20%. So the present value is 100, 1.20 to -4. That's how much I should pay today for this bond. Which is how much? Say again?
48.23.
Now that also happens to be the book value. So that's market value and book value. They're tied at this point. But it asks me for the book value of the market value in a year, in 2 years, and in 3 years. All right, well, let's think about this in 1 year. At time 1. Because this was based off of time 0. At time 1, I have 2 different setups. Book value is based on the interest rate at which the bond was purchased, the 20%. But we're looking here forward. We're at time 1, not time 4. So I'm going to raise this to -3rd power. What's this value? Now, here's an interesting thing. If you have this piece of paper and you've held on to it for a year, it's now worth 57.87, where a year ago it was worth 48.23. But if you want to buy that piece of paper at time 1, then it's only going to mature 3 years into the future, right? The market value would now be at a different interest rate. Because if I want to buy something that's 3 years out, not 4 years out, I have to use the spot rate for R3, not R4. And the spot rate for R3 is 1.15. And this is a different value. What's this one? Now that's a very interesting statement because that means that if I chose to sell this item right now, on paper, I can declare a profit. What about time two? How does this change again if I go to time two? So my book value is still going to be worth at 20%, but my market value will now be worked at what rate? Exactly, because our spot rate for 2 years out is 10%. So I get a book value of 69.44, and a market value of 82.64. If I do it again at 3 years, I'm now using 5% for the market value because I'm using the spot rate for something 1 year out in the future. So there's a substantial difference in what's happening here. Let me compare these numbers year to year. So let's start by looking at book value. Book value. Oh, you'll notice I didn't do time 4. Why didn't I do time 4? For both of them, I cash out, right? I earn 100 for both of them. Book value, time 0, 1, 2, 3, 4. Book value is 48.23, 57.87, 69.44, 83.33, and 100. What's my growth rate? How much did the book value increase each year? Exactly 20% each and every time. If I divide 5787 by 4823, I get 1.2. Same thing here. 6944 over 5787 is 1.2. All of these are 1.2, which means my book value growth rate is 20%, which makes sense. In every one of the calculations for book value, I used 1.2 every time. But let's do the same thing with the market values. What happens when I do the same thing with the market values? My market values were pretty different. What do I get the change to the market value to be? And if I keep going, I see a substantial difference here. The book value was consistently a 20% increase. Market value had a 1-year increase the very first year of 36%. But by the time I'm at the last year, it's down to 5%. As a matter of fact, this correlates exactly with our idea of forward rates. F12 and F23 and F34 and all that jazz. Here's a graph. Book values in orange, multiplied by 1.2 all the way up. That increase. But here's the market value. And it's a concave down curve here. It's slight, but it's bent. This is referred to as yield curve slide, the move away from book value that the market value undergoes. And the reason this is happening is because the term structure stayed the same as we moved forward. It didn't evolve or change in a fashion consistent with the forward rates. As a matter of fact, if I go through and compute forward rates, based on this term structure, using the calculations we did in the last chapter, you'll see these numbers are exactly the reverse of these numbers. The forward rates are the same as the market value changes in reverse. 36.34, 25.69, 15.245. And those are the numbers we came up with. If the term structure is static, the discrepancies between book value and market value are stark. But if the term structure is dynamic, then these will change. The higher the market rate versus the original book rate, the present value of the payments gets lower. Lower yield means a higher present value. I don't have to hold on to this for the entire time. By the way, these numbers that we computed right here, these are called the holding period returns. So if I hang on to it for a year at the beginning, I earn more money than if I hang on to it for that same year close to the end. Remember, a bondholder can choose to sell their security before maturity, but they don't have to. If they keep it to maturity, then the internal rate of return will be the book yield, no matter what happened in the middle. If they sell it in the middle, then the rate of return turns out to depend on the market value. By the way, whenever those spot rates change, my market value is going to change. If the spot rate were to suddenly go from 20 to 22%, well, then my price, because the spot rate goes up, my price is going to go down. Spot rate goes up, my price goes down. Yield is higher, my present value is lower. So if suddenly the spot rate changes, I overpaid. Our market price on day zero was $48.23. And that was based on the 4-year being 0.20. Okay, I happen to make this purchase first thing in the morning. Market's open in 25 minutes. Oh, sorry, 35 minutes. I'll buy it right now. But today happens to be the day that the Fed announces rate changes. And all of a sudden, by noon, they've made their announcement. And the rate changes. Then my market value should be different. What's my new market value at a spot rate of 22%? Which means I overpaid by a little over 3, right? A little under 3. 48.23 to 45.3. Did I not write down what? 14. Sorry. I overpaid. Okay. I overpaid by a little more than 3. But that's assuming they announce something that causes rates to go up. What if they announce something that causes rates to go down? What's going to happen if rates go down? Which means suddenly I underpaid and I got a deal, right? And in this case, what's this number? So I underpaid by a little over $3 and I make immediately. I could turn around and say, hey, I bought this morning. You want it? It's yours. The price is $51.58. I made $3 for every $100 I spent. A 3% profit that day, provided I watch for the spot rate change. Now, these numbers are exaggerated because you know as well as I do when the Federal Reserve announces something, motions in the Federal Reserve are quarter points, maybe. Spot rates move by 0.25. Sometimes they move by less. They used to do it all in fractions. They would announce either a quarter or an eighth. It's been a while since we had a rate change of 0.5%. Quite a while, as a matter of fact. Okay. These are risks, right? You buy a bond, there's a risk of default, there's a risk of the rate changes occurring, there's a risk involved here. In the late 30s, a guy by the name of Frederick Macaulay. I always screw up this guy's name. It's an A at the end. Frederick Macaulay wrote a paper studying interest behavior from 1856 to 1958. So what is that? 80 years of the study of how interest rates were going. And he addressed the idea of security of values and yields. And he said that only short-term loans can be imagined to be absolutely secure. And so he decided to measure security. How long this loan exists? What is the duration? So I'm going to use this duration length idea. And once I use it to measure the security, I can then compare these things. Okay. Let's think about two deposit accounts as an example. My loan has a present value of 100. The interest rate is 10% effective APR. I'm going to do this with annual compounding. Since I've given it as an APR, I don't have to do anything at all to that. I'm not worried about effective anythings. Here's loan one. You make the loan of $100, you get $259.37 10 years from now. Absolutely nothing else in the middle. You just get ka-ching, one payment, $259.37 at 10 years. Why would it be that number? Where'd that 259.37 come from? 259.37. As a matter of fact, that's exactly what this is. This number is 100, 1.10 to the 10th. Perfect. Loan two pays 100 in 1 year and $23.58 in 10 years. What? Why the hell would you do that? Well, let's think about this. If I put $100 in the bank, if I make that loan right now, I give you $100 at 10%, what do you owe me at the end of 1 year? But you pay me 100. What's left behind? And I hold that for another 9 years. What's the future value of that $10? Oh, that's 10 times 1.10 to the 9th, which is lo and behold, it is. Now, if you're making this loan and you're getting the money, I think you probably want the first one rather than the second one. Yes? You're going to make more money if you can afford to leave that out there for all 10 years. This pays money much later than this one. This one pays more money up front. So if I'm paying money earlier in loan two, I can think of that one really as being shorter than loan one. Even though both technically last for 10 years, the cash flow in the first one is way late, and the cash flow in the second one is more early. So Macaulay said, since only short-term loans can be thought of being absolutely secure, I'm going to think of the idea of loan one as being a longer loan than loan two. Now, this idea of longer is called the Macaulay duration, or just the duration. Of our loan. Now, Macaulay originally defined this for a flat term structure. What does that mean again? To have a term structure that's flat? What's a flat term structure? This thing is our term structure, our list of spot rates. What's it mean for our list of spot rates to be flat? All the way through. RT is the same for all T. It can be adapted to fit things that aren't flat when we have a fixed set of cash flows. Where would I have a fixed set of cash flows? Oh, I don't know. How about an annuity or a bond with coupons? So the real question is, what is duration? How do I compute it? And what does it tell me? Well, the best part is that it's just a weighted average. But the weights are based on the present value of the payments. Okay. The duration definition comes in two flavors, one for flat, one for non-flat. But the idea is the same. Definition. The Macaulay duration, DMAC. Now, sometimes it's specific to a rate. Our flat structure would have one interest rate for the whole time, in which case I'll call that interest rate I. If I'm looking at a non-flat structure, I'll just omit this. For a flat structure, for the moment, I'm going to assume that everything is done in years. Although if you want to change these to another unit, that's still fine. We just prorate everything into those units. So I could do this by months, I could do this by weeks, I could do this by quarters. I just have to have a uniform behavior between my interest rate and my cash flows and my times. If they're irregular, you could find a least common unit and then have a bunch of intermediary ones that had value 0. So if I had something in week 1 and nothing until week 6, I could have cash flows in week 2, 3, 4, and 5 of 0 and have that carry through. Oh, good Lord, look at this ugly mother. What the hell? You having any problems with technology? The only thing I've had is that light keeps flickering. Everything else has been fine so far. Sorry, Bernie. What's going on here? Wait a second. This number right here, KT times 1 plus I to the minus T, that's the present value of the payment KT. This extra T right here says that stuff that is further away contributes more to the duration. So we're taking the present value and multiplying by how far out it is. The closer it is to now, the less it's going to weigh. The further it is from now, the more it's going to weigh. May I borrow your baseball bat for a moment, Joe? It's the weirdest thing I can do. But here you go. This is exactly the idea. Let's consider the butt of the handle to be time now. Payments that happen out here, further away from now, way more. They contribute more to my average. So where's the center of all of these payments? It's out here, isn't it? A weighted average. If I have more payments further away from today, they should count more. On the other hand, if I have more payments close to today and fewer payments out in the future, I should have a duration that's short because the weight will be down here. And that's really what this is. It's a torque from a physics perspective. And I know if you took Calc 2, You saw that example for center of mass in chapter 8. It's the same equation. It's just discrete, not continuous, which means I could turn this into an integral if I really wanted to. I don't, but I could. Okay, wait a minute. This version fits our example. Our example had a flat term structure. Our example had 10%. Loan one. Loan one had one payment. It was going to be a payment of, I wrote that down, $259.37. In 10 years with a rate of 10%. What's the Macaulay duration? Well, since there's only one payment, this is not even going to have a sum in it. I can use exactly this formula, but there's only one payment. So the Macaulay duration at 10% is 10 times 259.37 times 1.10 to the negative 10 divided by 259.37 times 1.10 to the negative 10th. I don't even have to do the math. What happens? Because these two things cancel, top and bottom. This, by the way, is true all the time. If you only have one payment, then the duration is the term for that payment. But let's look at loan two. Pays 100 in 1 year and 23.58 in 10 years. Again, with a flat term structure, I equals 10%. Let's work out the duration for this. Well, my first payment, 1 times 100 times 1.10 to the negative 1. My second payment is 10 times 23.58 times 1.10 to the negative 10th. That's divided by, no times, 100 times 1.10 to the negative 1 plus 23.58 times 1.10 to the negative 10. This time I need to do the math. What do we get? Again, before I do any math, my brain says the duration should be much closer to 1 than it is to 10. Because I've got a lot more being paid at time 1 than I do at time 10. I like that. That's what I got as well. 100 divided by 1.1, 235.8 divided by 1.1 to the 10th. Yeah, that's exactly what we have. But notice that's a lot closer to 1 year than it is to 10 years. As long as all my cash flows are positive, I would expect cash flow at time 1, cash flow at time 2, my duration to be somewhere in between. And if I've got cash flows that vary in size dramatically between these different times, as long as they're all positive, I should expect that weight to cluster around the largest cash flows. Mortgages used to all have balloon payments. They were not level payment annuities. You would pay on a $25,000 loan, you'd pay, I don't know, $200 a month. And then at the end, you'd still owe $15,000. And so that would have a long duration because of the long payment at the end. But those mortgages were usually 5 or 6 years. It wasn't until the advent of the 30-year mortgage that we started looking at level payment behavior. I don't know if Macaulay intended to use this to calculate bond prices due to interest rate changes, because there's a picture in the textbook of the 10-year bond rate since the 1700s. By the way, if I go to the Federal Reserve database, the Federal Reserve database only has this information back to 1962. 1962 is here. So as you can see, there's been a lot of changes since 1962. But before that, bond rates were fairly steady. They didn't spike very high. They didn't go very much above 8%. And then we had this huge spike in the 1980s. This was precipitated, by the way, of international changes to the monetary funds. We went off the gold standard. We changed the way we banked. That happened in the 1940s. Right here. And so the dollar started to float instead of being a fixed back currency. So almost all of this can be traced back to changes in monetary policy. Okay, this is the version for a flat rate structure. What happens if it's not flat? Well, then I have interest rates RT, where RT is the spot rate at time T. So spot rate is the annual rate as of time 0 for a 0 coupon bond maturing at time T. So the price, the interest rate today for a 0 coupon bond in 1 year, 2 year, 3 year, 4 year, however many. Then I'm going to change one thing in my definition. The duration is the sum T equals 1 to N, T times KT times 1 plus RT to the negative T over the sum without the time. It's the exact same idea. The only difference is I've replaced I by a variable rate. And this is a weighted average on time. Now, the problem is that that huge volatility spike that happened recently, relatively recently, it happened in the last 100 years, meant that this definition really kind of lost its place and utility once we hit the 40s. Now remember, Macaulay did this in 1938. So when Macaulay did this, he was looking at rates that had been fairly uniform, even routinely declining. Post that, oh shit. So Macaulay had a problem. And the Macaulay definition didn't exactly work as well as we wanted it to. So several people said, we need to fix this. We need to modify this. I'm pretty sure the modified duration is set up only for flat rates, but it can be worked out functionally for a modified non-flat rate. So I'm starting with the assumption I've got a flat rate. Again, cash flow is payments K1 through Kn, at times 1 through n in years. Or whatever common unit I'm using. Present value, we're going to call that P of I. And that is the sum j equals 1 to n of, I'm sorry, that's not j, that's t. T equals 1 to n of k t, really? 1 plus I to the negative t. That's our standard present value calculation. The modified duration. D mod I is a derivative. And it's not just any derivative. Once again, it's a derivative I made particular mention of back in Calc 1. This is negative, the derivative with respect to I, of the logarithm of P of I. This is a logarithmic derivative. Which is why I know I can apply this to a non-flat structure, provided I can write this function P of I. Now, again, present values go down when rates go up. Since present values go down when rates go up, the derivative P prime of I should be negative. Present value goes down as rates go up. dDi of Pi is negative. As the rate increases, present value goes down. That's why I need this minus sign right here. Because I want duration to be a positive idea. By the way, because of that, we're always going to use the word modified when we talk about this version of duration. Macaulay duration is in years, but modified duration isn't. That 1.818 number that you gave me, Adam, that's years. 1.8 years is the duration of that loan from Macaulay's perspective. Modified duration has a different unit. And it's really kind of gross. Change in present value per dollar of present value, which is really percent change in present value. So modified duration, wait a second, that's the change in that per change in APR. Oh gods, this is measuring two changes against another change. Dear Lord, that's disgusting. The units for modified duration, change in present value per dollar of present value per change in interest rate per year. Because we're using a derivative here, that derivative has these units, and then I'm dividing by P of I. Oh boy. All right, wait a minute. The present value was P of I is sum kt 1 plus I to the negative t equals 1 to n. That was P of I. What's the derivative with respect to I? Wait a second. Kt is a constant. The only I appears in here. This is power rule, right? I'm looking at change in I. All right. So that's sum kt minus t stuff to the minus t minus 1. Then I take the derivative of the inside with respect to I, but that's 1. Oh, there should be a minus sign more clearly visible there because it's minus t. Hey, wait a second. Wait a second. Let's put that negative sign out front. Let me split off that 1 plus I to the negative 1 power. I'm going to take this number, which is a constant, and put it out front. That summation looks awfully familiar, doesn't it? Where have I seen this before? Just the summation part here. Aha, that's part of the top here, isn't it? And this is our present value, isn't it? So if I do the modified duration here, negative derivative with respect to I, P of I, over P of I get, I lose the minus sign because of this right here. I get 1 over 1 plus I times the sum t kt 1 plus I to the minus t over sum kt 1 plus I to the minus t. That's 1 over 1 plus I times the normal Macaulay duration for I. So the two durations are related. Macaulay duration in years is related to the modified duration in years divided by growth rate. Years divided by growth rate. I like that unit better. That kind of gives me a better way to look at this. Matter of fact, we have two loans, right? We have loan 1 and loan 2. Loan 1 had a duration for Macaulay of 10, and loan 2 had a Macaulay duration of 1.818. So let's look at the modified duration. The modified duration for that first loan is 10 divided by 1.1, which is 9.09 repeating, I think. It's 100 over 11. I think that's 9.09 repeating. And then our second loan, 1.818 divided by 1.1, has a duration of 0.818. So please notice that the modified duration is shorter than the Macaulay duration because we're dividing by a positive number bigger than 1. Our 1 plus I, our growth rate right there. As long as our economy is growing, modified duration will be shorter. If our economy is contracting, we have a whole different process. Thud. duration. Here are the formulas we've just been using right here. Notice they've written it in terms of V instead of 1 plus I. Big deal. I told you I didn't like using V, but there's these formulas exactly the way we want them. Modified is 1 over I times the Macaulay duration back here. There's our version of it as a logarithmic derivative. We'll talk about this one in a little bit. Questions? This is a weird perspective. Now, my goal is to then apply this idea to all of the bond structures we've been looking at. Zero coupon bonds, and to figure out how I know whether or not I have a cash flow that will be sufficient for me to pay all my liabilities moving forward. I need to balance my cash flow. But that is definitely not going to be done today. We'll pick this up on Thursday. I will see you all then. Reminder, the chapter 6 homework is due then. If you've got questions, come bug me.